Okay, we'll go ahead and get started. We left off on page 5 of the chapter 10 worksheets. So this was a limiting reactant problem. And how do we know that it's a limiting reactant problem? If we're given just one reactant mass and we're asked about a product, then we just have that one calculation to do. But in this case, we were given the mass of 2 different reactants. So when we see the mass of 2 different reactants, we need to do a separate calculation for each. We need to do 2 parallel calculations to find out how much mass could be produced from each of them. So each of those mass-to-mass calculations goes mass to moles, moles to moles, moles to mass. And then we're going to choose the smaller amount. So in this case, we decided that the limiting reactant was HCl, and that the theoretical yield, the amount that's produced, was the smaller amount between those 2 calculations. We're going to do the same thing with this next problem. Here we have a combustion. We've seen this one before. We're starting with 50 grams of propane, 50 grams. And we're starting with 150 grams of oxygen. We are going to look for the mass of CO2. How many grams of CO2? So I've completed my mass-to-mass calculations, and now we have to answer the questions below. Let's take a look at the significant figures first. In red, we started with 50 grams of propane, and that was 50.0 with 3 significant figures. So in my answer, I've underlined the 9. That's the 3rd significant figure. Notice in the brown, we're starting with 150.0 grams of oxygen. That has 4 significant figures. So I'm going to underline the first 7, because if that is our final answer, then it has 4 significant figures. It's a little bit tricky. All right, how do we decide which one's the correct answer for the theoretical yield? We're going to pick the smaller amount. We know from those starting materials, from those 2 calculations, we only expect 123.8 grams of CO2 to be produced. Now I've rounded that value to the 4 significant figures. So if I was going to proceed with future calculations, I would go back to using the unrounded value, even though I presented a rounded value as my final answer. That's why I really like the underline system, where you keep track without doing the rounding, so you keep all the information. The next question is, what was the limiting reactant and what was in excess? The limiting reactant is going to be the starting material that gave us that answer. So our limiting reactant is going to be oxygen. Even with 150 grams of oxygen, to only 50 grams of propane, it was still limiting. And that means that the excess reactant was that propane. So just to review, how do we know it's a limiting reactant problem? We know because it gave us two of our reactants. So we have to find out which one is going to produce the smallest amount of products. We're going to move forward now. Percent yield is an indication of how much actually forms. The amount that we actually obtain can sometimes be lower than what we expect, right? So the theoretical yield is what we expect. Now let's say we're looking back at this problem and it turns out that reaction was oxygen limited, so it did not burn completely. So we may not have produced all of the CO2 in that problem. Maybe there was some propane that did not get burned. And so we would expect our actual yield, it might be a smaller value. So we can quantify what that yield was. So we're going to take our actual yield that's given in the problem. Maybe you're doing a precipitation reaction, so a totally different example. You're doing a precipitation reaction, you want to get that solid, and then you have to strain out through a filter and spread it out to dry it, and then you go weigh how much solid was there. So you might weigh that and get it in the lab conditions as well. So this value is given in the problem or measured in the lab. The theoretical yield is your expected value from the mass-to-mass calculation. So in reaction above, our theoretical yield was 123.8, or I'm going to keep the unrounded value because we're going to need to use it again. So 123.77. Now, what if we caught all of that carbon dioxide maybe on a filter or collected it in a cylinder? So let's say we captured that gas and we measured the mass and it was only 70.6 grams. We would be able to quantify how that reaction proceeded using a percent yield. So we will take, using this equation here, we'll take the actual amount over our theoretical yield, and we're going to keep all of those digits. So that was grams of carbon dioxide we expected, and we're going to make it a percent. So let's go ahead and calculate that. It'll have just three significant figures, and I get 57.0% yield. Now, could we ever have a yield that is greater than 100%? We don't expect it, but sometimes it can happen. So one example would be if you have a precipitation reaction, so you form a new solid and you spread it out and you dry it and you go to weigh it, maybe the lab is ending. So you put it on the balance and it weighs more. Maybe there's still water inside there. So maybe your percent yield is higher than you expect because you're measuring the water too. It's possible to get values that are greater than 100%. So don't always just flip it. You have to think about, did I put the actual over the theoretical? Let's do it again. Let's take a look at this question. Now, is example 3, is that a limiting reactant problem? No, it reacts with excess carbon monoxide. So there is only one reactant given. Excess means there's extra. So we only need to do one reactant, run one mass-to-mass calculation here. Remember to look for what your target is when you do your mole-mole relationship. And then we'll fetch those numbers. I like to fill in the units and then determine the numbers that make that true. Okay, maybe they're trying to recover the iron metal. How much did they actually get from that process? Now, in the next section, we're going to look at another way to get to moles. In this case, in these calculations, we use the mass and the molar mass to get to moles. That works well for solids, but when we start working with aqueous solutions, we have kind of an easier way to get to the moles. And so that's what we're going to need to do for our next lab and for the pre-lab for our next lab. So we'll do a quick review of solutions. We saw some of the solutions terminology in chapter 13 when we were looking at solubility. We looked at precipitation reactions and solutions, and so we did a little bit of assigned reading from chapter 13, which was solutions. And here we're seeing it again in chapter 10. So solutions have different components. So something that's present in smaller amount is the solute. The thing that's present in greater amount is the solvent. And for us, that's usually water. And that will give us an aqueous solution. So aqueous means it's dissolved in water. And we can talk about a concentrated solution. That is something that has a large amount of solute. For example, if your coffee is just too strong, or if you have lemonade that's very sour, is too much lemon, that would be a concentrated amount. A dilute solution has just a little bit of solute. So that might be a drink mix that doesn't have enough of your flavoring. So dilute has a small quantity of solute. So in general, our concentration is the amount of solute over the amount of solution. And I like to think of that as the total solution. In chemistry, we often will have things that are just two components, just water plus your solute. But there are also solutions that have more components in them. So there are a lot of different units for concentration. We're going to focus first on the easiest one for chemistry, and that is molarity. Molarity is moles of solute out of liters total solution. So it's really important to pay attention to the labels and make sure that those are correct. Now the other thing about molarity is that you have this capital M, and that has two units in it. It has moles on top and liters on the bottom. So whenever you see that capital M, I encourage you to go ahead and write in moles on top and liters on the bottom so that you don't forget one of them. Now we see these square brackets. That implies molarity. So when we looked at our acid-base reactions and we said, okay, Kw was 10 to the minus 14th, and that was the H plus times the OH, that implies that these are molarities. This is moles of OH per liter total because of the square brackets. Okay, so let's do a couple calculations and get comfortable with molarity. So if we dissolve sodium chloride in water, and this is total volume of solution, that is our total volume, we need to find the molarity. How many moles of solute The solute in this case is sodium chloride, and we need liters total. So we can just plug that in, right? We need to write the units we're looking for, and that will help us put the pieces together. So those moles are going to go on top, and that volume goes on the bottom. We have 250 milliliters of total solution. Well, we need to get rid of the milliliters and go to liters, and then we'll get one value. So 1,000 milliliters on top to 1 liters here. That gives me 0.154 molar solution. Now we're going to name this. This is 0.154 molar NaCl solution. We name it for the solute. So don't forget, it's not pure sodium chloride. This is a mixture in water. We just name it for the solute, kind of like we would name lemonade. It has lemon juice, and that's the thing we can taste, and so we're going to call it lemonade. It's not pure lemon juice, right? So we're going to name it for the solute, but recognize that it's dissolved in water. Okay, what about this next one? Find the molarity. So that's moles of hydrogen peroxide, that's H2O2. And then here they give us, we need liters of solution. So this has the label that we need. That's the solute, so we'll put it on top. And that is the total solution, so I will put that down here. All right, what do we need to do to make that conversion? Go ahead and use your dimensional analysis to line it up. Let's see, we need to get to liters down here, milliliters up here. Okay, that should cancel out everything, and I'll show that canceling. These guys, grams, so we end up with moles per liter. All right, that had 3 significant figures, so when I round that, that's going to flip it up, and I'll get 980 molar peroxide solution. So that's kind of the outline of how these go. We, of course, have to go backwards and forwards. So let's take a moment to write these factors with a clear unit and label on the top and the bottom. So remember that the capital M means moles per liter. So here we have 2 factors that we can write. Moles on top, liters on the bottom. So that is, and do you remember what nitric acid is? That's one of our strong acids, HNO3. So 6.00 moles of HNO3, that's our solute. In means in the bottom, 1 liter of solution, and that's the total solution. So another way to say that, I could say 1 liter of this nitric acid solution must contain 6.00 moles of HNO3. So let's do the same thing for this one. Okay, so we can write those molarities either way we need them. This way we can put them together in dimensional analysis to make that conversion, to get how much solute we might need. So this is our new way to get the number of moles. When we have this molarity, moles per liter of solution, we can multiply it by the volume. So you might think about maybe hot chocolate. There's the concentration of hot chocolate that we like to drink. It has a certain amount of chocolate, a certain amount of sugar. If you want to find out how much chocolate you just drank, you have to multiply by, was it a small cup or was it a large cup? So anytime we get the volume times the molarity, those are going to cancel out and you're going to get moles of solute. So we'll be using that, and it's a little bit easier than doing the mass and the molar mass because you have to calculate your molar mass. With a molarity and a volume, they're usually given in the problem, or maybe you have to solve for one. Let's take a look at how many moles of sodium chloride are in 1 liter of 1 molar. Now here's the word of. Of usually means multiply. So when you have a molarity connected to a volume by the of, they're going to get multiplied. Here we have 1.00 liters of solution. And so I'm going to multiply by that molarity. And I'm going to write out the units for it so it's really clear so you can see it. 1 mole of NaCl in 1 liter of solution. 1 mole of NaCl. Math is easy on that one. All right, now we're going to go one step further and find what mass. So how many grams of NaCl do I need for that? Well, we can still use dimensional analysis, and that tells us what to do. We're going to go weigh out on the balance. We'll just weigh out 58.44 grams of sodium chloride. So we've seen all of those pieces together. The new part is using the volume times the molarity to get moles. This is the easiest way to get moles when we have an aqueous solution, something that's dissolved in water, aqueous. So let's do a couple problems, and then we'll talk about how to prepare a solution. So in this case, we're having someone drink baking soda. Not so tasty, but it helps with the condition acidosis. So we want to know what mass of baking soda is present in 1 cup. So let's just go ahead and use the milliliters here. Milliliters of solution. And then here's the of, we're going to multiply times that molarity. So write that molarity out with units, moles on the top and liters on the bottom. All right, what else do we need to do here? We have our milliliters to liters conversion. Then we need to cancel out moles of sodium bicarbonate in the bottom. And we can use the molar mass to get to grams. All right, so to remedy the acidosis condition, they drank a cup of solution that had 4.5 grams of bicarbonate in it. So we canceled out all the units along the way. Now, how do we make these solutions? We're going to go back to that previous example with the sodium chloride. So we determined that to make 1 liter of 1 molar sodium chloride, we need 58.44 grams. So we're going to use that here to talk about how we make a solution. So we go in the lab, we weigh out 58.44 grams of sodium chloride. Here's our flask. This is a volumetric flask. has one line, so only one volume. When we work with a cylinder, it has graduations. It's got all those marks, so you can measure any volume in that scale. For a volumetric flask, it's precisely calibrated to measure just one volume very well. So this is 1.00, usually 4 liters. So we add some water, we add our salt, we mix it around to get it dissolving, and then we fill it up to that line. And that's how we'll make a solution. So I want to refer you to the next lab, is the kinetics pre-lab. It follows this same kind of a calculation. You're going to design a solution. So you need to make your solution. That means you're going to have to calculate how much to start with, weigh that out, and then we're going to make the solution for the lab. So that's part of the pre-lab, but it looks a lot like this one. There are other units of concentration. We're not going to focus on them as much, but they're really just unit conversions. Now we're talking here about the mass percent, so it's another kind of percent. We saw percent by mass for elements in a compound, and now we're looking at a mass percent concentration. So it's a concentration, so we still have solute over solution. So we have mass of solute, mass of solution. But remember, if we're making solutions in the lab, we usually just have two things. So that's going to be the mass of the solute plus the mass of the solvent. In this picture, we have the line. We just fill it up to the line so we know the total volume. But maybe you don't have a volumetric flask and you have to weigh the water. We might have to figure out how many grams of water do we put here. So it's really important to pay attention to the labels as well. All right, so if we're going to dissolve 10 grams of sodium chloride in 250 grams of water, let's calculate the mass percent concentration. So which one is the solute and which one is the solvent? The water is the solvent. So we're going to take 10 grams of NaCl, the solute, and what do we put in the bottom? We need the solute plus the solvent. So this is going to be 260.0 grams total. And that's still named after the solute. All right, let's do one more before we end our time. What is the mass percent concentration of a solution made with acetic acid in 150 grams of water? $157.95 grams total. And that's about 5% acetic acid. I think that's about what we see in vinegar. This ends up with 3 because of this value.